Alright, today we are going to work on multiple angle and product to sum formulas, and the nice part about this section, it is a good amount of formulas, and I guess that's a good and bad thing, because, let me go back to the title so you can, if you're copying that down. These formulas, essentially, if you know the formula, they're pretty straightforward when you need to use each one, because again, you're using this formula when we have sine of 2u or tangent of 2u or cosine of maybe a different variable like 2 theta. So, and cosine actually has 3 different formulas, so you can use either one, whichever you think is going to benefit you the most. So pause the video, take a second to copy these down, and I will see you on the next slide. All right, so here, the directions, same as section 5.3, where they want us to solve for x. The problem is, when we solved for x, we never had a problem that had an x and like a cosine of x and a sine of 2x. So we are going to be using that double angle formula, and on the last slide, you saw that the sine of 2u is equal to 2 sine u cosine u. So that substitution is exactly what I'm going to, this is the piece I'm taking out. I'm taking out sine of 2x. I'm going to be replacing it with, copy over 2 cosine x, plus now the sine 2x gets replaced with 2 sine u, cosine u, and it still is set equal to 0. And from here, I would hope, well, I shouldn't be using u, should be using x. And from here, I would hope you have enough information to be able to solve this for x. And what I notice is we have a GCF. We could take out 2 cosine x, and that would leave us with 1 plus sine x equals 0. Here we're using zero product property, ZPP. 2 cosine x equals 0. 1 plus sine x equals 0. So here I can essentially divide both sides by 2. That's still going to read cosine x equals 0. Where does cosine equal 0? So on the unit circle, cosine is equal to 0 at 2 places. That's going to be at pi over 2 plus 2 pi k. It's also going to happen at 3 pi over 2 plus 2 pi k. You'll notice if this answer was in the back of the book, it would say pi over 2 plus pi k, because that's an equivalent way of writing it, although I'm okay with either. Here we're going to read sine x is equal to negative 1. Sine is equal to negative 1, also at 3 pi over 2 plus 2 pi k, which means this answer is just a repetition of this answer, so you can kind of leave it out or just state it twice. There we go. Did I skip one? Nope, we're all set. Okay. All right, so here we are asked to calculate sine 2 theta, cosine 2 theta, and tangent 2 theta, given all we have is that cosine theta is equal to 5 over 13, and this is saying that we are in quadrant 4. So that tells us about our sines. Like, I know cosine is positive in quadrant 4. And to do this, I essentially already know x and r. So we've used it before. X squared plus y squared equals r squared. So 5 squared plus y squared equals 13 squared. I think you could probably solve this on your own and get y is equal to 12. The question is 12 positive or negative? Well, we know sine in quadrant 4. We know that sine theta is going to be equal to negative 12 over 13. We also know tangent theta. Tangent theta is y over r, which would be negative 12 over 5. This is all information we are now going to use to be able to solve using our formulas. So thinking about sine of 2 theta first, from the last problem, we already know sine of 2 theta is the same as 2 sine theta cosine theta. Well, if I take this this piece of information, I'll move my work down over here. I know sine theta. Sine theta I have right here. Cosine theta they gave to me, and I'm going to substitute both of them in. It's 2 times negative 12 over 13 times 5 over 13, and here it's just multiplying fractions to get to our answer. That's going to be 24 times 5, so that's 120, negative 120 over 169. Negative 120 over 169. Now we're going to do the same thing for cosine. And again, for cosine, you have 3 ways to do this problem, so don't feel like you have to do it my way. I'm going to use the problem 1 plus sine squared, 1 minus sine squared theta. Forgot the 2. There's the 2 in the formula. And now I use, again, this information right here. I'm going to substitute it in. It's to get cosine 2 theta, all I do is substitute in, and I do 1 minus 2 times negative 12 over 13 squared. And negative 12 over 13 is going to be 144. So 1 minus 144 over 169. 2 times that, sorry. So now I would be looking at 1 minus, that's going to be 288 over 169. So if I look to get like terms here, or like denominators, I could call this 169 over 169. If I subtract that, give me a second here, if I subtract that, I should get 119, negative 119 over 169. Negative 119 over 169. Okay, that leaves us, the last one is to find tangent 2 theta, and there's a formula for tangent 2 theta as well. It's 2 tangent u over 1, so here, 2 tangent theta over 1 minus tangent squared theta. And all we have to do is substitute in. Here, this is the information I'm substituting in. The top of my fraction will read 2 times negative 12 over 5, all divided by 1 minus negative 12 over 5 squared. So I know this is a complex fraction. We've done these before. Negative 24 over 5 divided by 1 minus, that's going to be 144 over 25. So let's get common denominators here. If I think of this as 25, I think of that as 25 over 25. I could now subtract those. That's going to be 119, negative 119. So I have this fraction, negative 24 over 5, all divided by negative 119 over 25. And this is, you cannot leave this answer as a complex fraction. I'm running out of room here a little bit. So let me pick this up and slide it to a new area. So a little more room to work. The last part to this is a division problem. In the key, if I am dividing by negative 119 over 25. That's dividing by a fraction. The easy way to do that is to multiply by its reciprocal, negative 24 over 5 times 25 over negative 119. So first off, I see 2 negatives. I know that's going to make a positive. I could simplify a little bit here. I know that's going to be 5, so 24 times 5 is negative 120. I'm sorry, not negative. I knew it's positive. Over 119. All right, so here we're going to do a little proof. For this proof, I'm not telling you you don't need to memorize the triple angle formula. This is just an application of the double angle formula. This is an application of sine theta is equal to 2 cosine theta sine theta. Because what I'm thinking here, I see this as sine of 2x plus x. So that's a similar way to write this. And I could use, now, the other part to this problem is it also uses the a sum of sines from the last section. It uses that sum of sines formula. So the other formula I am using from our last section, sine u, that a little better, sine, sine u plus v sine u cosine v plus cosine v sine u cosine u sine v. Saying everything wrong. Okay, looks pretty good there. So now I have this written as the sine of a sum, and I'm going to expand it using this first formula. And the way that's going to work is I will have sine 2x cosine x plus cosine 2x sine x. And now I can use two of the formulas. I can use the formula right here. I can start using my double angle formula, which I had incorrectly written there. So let's do that. And I can also use the cosine formula, which I didn't actually put on the board yet. So let's expand this. The first one is going to be 2 cosine x sine x, and then I'm going to recopy over this cosine x. That's the whole first term. The cosine of 2x, we can use the formula 1 minus sine squared. 1 minus 2 sine squared, I believe. 1 minus 2 sine squared. 1 minus 2 sine squared x, that needs to be in parentheses, times sine x. And now I could simplify a little bit further, and I could call this 2 cosine squared x sine x, plus here, if I do some distributive property, that's going to be sine x minus 2 sine cubed x. At this point, you've written it in a way that it uses only sine x and cosine x and some exponents. If you want it to be fancy and you want to simplify this down a little bit further, you could use your Pythagorean identity. Cosine squared x is equal to 1 minus sine squared x. And we could substitute that in right here. And this would read 2. I'm bringing this sine x over, and then I'm substituting in my Pythagorean identity. And the reason I'm doing this, and copy over the rest, is because I'm going to see some like terms when I distribute this. I'm going to see like terms. So 2 sine x minus 2 sine cubed x plus sine x minus 2 sine cubed x. And we can now, in a much simpler fashion, we could call this 3 sine x minus 4 sine cubed x. So in our when we start the next video, we are going to start using the power reducing formulas, and these power reducing formulas need to go in your notes. So as you close this video, I would copy this down, and I will see you in the next video.